Okay, I guess we are live. Fine. So hello all. Welcome to the second class of this course on generative modeling using VAs. Last class we discussed some very basic probability related stuff just to get things rolling and catching up on basic but important concepts and setting up the foundations. So we'll do a quick recap of what we had done last class. So first of all, we started with this probability, idea or the inherent assumptions that we generally take when calculating these probabilities using our everyday thought process. And then we looked at things like conditional probability, independence, and all of that sort of thing. Then we went on to move to the idea of random variables. What exactly is a random variable, and how does that? What are the different types of random variables? What are probability distributions associated with with each type of random variables? For example, we have probability mass function, cumulative distribution function, and then probability density function for absolutely continuous random variables, and then some examples of them. We then went on to understand what properties are there, which are going to be interesting for the course at least. One is the idea of support, then the expectation of a random variable, that is on average, what value can you expect it to give, and then the variance of a random variable. And in this variance calculation, we saw something like expectation of x squared, which was something like expectation of a function of a random variable. And we dive deeper into it and try to understand what could that mean in terms of the distribution of the random variable itself, the one for which we have a function of. Um, then we looked at this idea of multiple random variables and thought about this random vector sort of a thought process. And we discussed something like the joint distribution of two random variables. For example, there is mentioned here pxy of xy, right? So where we say that okay, how are these two random variables occurring together? What is that probability space look like? And how to define independence of random variables in the first place. So what we had seen before was independence of events, and how does that transform to the idea of independence of random variables, right? And then we touched upon this idea of what a PD and a PSD matrix is, and the idea being that we will go ahead and use this idea of PD PSD matrices in constructing an invertible matrix, right? Invertible variance covariance matrix. And why was that required? Is because of this idea of multivariate Gaussians, where if I have a random vector, let's say x, which is distributed as a Gaussian random variable with mean vector mu and variance covariance matrix of capital sigma. So the probability distribute the density of x follows this particular form, and here as you can see we need an invertible matrix. So how do we make sure that I mean going forward we will have to make sure that this sigma is always invertible. So hence we touched upon this idea, a brief idea about how one of the methods could be that we could make sure that this sigma is a PD matrix, right? And we'll see exactly how people have tried to solve this problem, and what exact methods are out there. Okay, so today, so a brief recap. So today we'll continue our discussion on this Jensen's inequality, and we'll complete the proof today of what this is inequality is. So last time we spoke about something called a Taylor series expansion of a function, and we said that let's say if I have a function f of x and it's if it is infinity differentiable at let's say some point a, then f of x can be expanded as this infinite series of terms, which is f of a plus x minus a f dash a and so on, right? And some very standard examples, some trivial non like examples are shown here. Then we also talked about this idea of error term, right? For example, let's say if I have access to only the first or the second differential of a function, and I cannot go up to infinite differentiation terms. So then how do I understand how much of I am from this, the value, the actual value at x. So the Taylor's remainder theorem tries to, give us some sort of an estimate of the particular error. Okay, so we'll do that. We'll just look at the statement and some formulation for this, and then we also discuss the idea of convex functions, right? And convex functions in its most basic definition is something is defined like this, right? So let's say we have any 2 points, let's say x and y, and if I have a function f of x, it is said to be convex if it obeys this particular sort of a law, this particular relation for all x and y in its domain, and for all this theta being in 0, 1 inclusive set, right? That is f of theta x plus 1 minus theta y should be less than or equal to theta times f of x 1 plus 1 minus theta times f of y, right? And what that means geometrically is that, let's say if I have 2 points x and y, theta x plus 1 minus theta y talks about any point between x and y, right? So for different values of theta, I'll keep on going. I'll have different values that I will span from x to y, right? And so then let's say if I have at x I have this value f of x of the function, and y I have this value f of y of the function. So what we are saying is that the function value will be less than the same interpolation that follows on the y-axis, right? So this line will always be more than the actual function, that is f. So if it obeys this sort of a property at all points x and y, then we say that f is a convex function. Okay. And we stated what Jensen's inequality was, right? So it says that, let's say if I have x is a random variable, right? X is a random variable, and I have g of x, which is a function of x, and let's say if g is a convex function, then the expectation of g of x, right? That is more than or equal to the g of e of x. E of x is the expectation of x. When I apply this convex function on the expected value, that value will always be less than or equal to the expectation of expectation after applying this g on every possible value of x, right? That is the meaning. That is the statement of what it is shown mathematically here, right? So we'll come back to this Taylor remainder theorem, and what it states is basically something like this, right? So let's say if I have f, and let's say if I have f is double differentiable, that is I can differentiate twice, right? So what Taylor's remainder theorem tells you is that f of x is equals to f of a plus x minus a times f dash of a plus x minus a squared by 2, but with this f double dash of c, where c is some point between x and a, right? And the c in some ways captures the how off the value from x, how off the value of the function f at x is from this particular linear interpolation that we have taken right? So this is the Taylor remainder theorem. Now let's try to apply this to our use case and see how we can come up with this Jensen's inequality proof, right? So let's say if f is convex, what sort of and we also touched upon this point. So any thoughts on which term we can start off with analyzing first here? So if f is convex, which term here is uh, you know uh, uh, very intuitive to understand how it will affect? Any thoughts? So last class we discussed something like what will happen to the second derivative for a convex function. Anyone remembers what was the short discussion we had there? If f is convex,
Greater than 0.
greater than 0, right? And to be bit more precise, I will just say that if f is convex, f double dash will be greater than or equal to 0, right? That is for all x which belongs to the domain of f, right? So when this happens, and we know that x and a both are here, real values and stuff. So x minus a squared is again a positive quantity, and this we have seen is a non-negative, both are non-negative quantities. So what will end up happening is that this term now becomes f of x. I can write it as f of x greater than or equal to f of a plus x minus a times f dash of a, right? So we have got this greater than or equal to part clear. Now let's see how we can, move forward. So now let's say if x is, for example, a random variable, right? So, mm, mm. so now if x is a random variable, let's say I will call x, capital X, as a random variable, right? So then I can write f of capital X is greater than or equal to f of a plus x minus a f dash of a. So mind you, here x is a random variable, so f of x, this is also random, right? Here x minus a becomes a random, so because x is a random variable, so this whole expression also becomes a random variable. So we are comparing two random variables, and that is basically with this relation that some random variable is greater than or equal to some other random variable, right? So we'll use a simple theorem to help us understand what could how can we compare the expectations of such quantities. So let's say if x is greater than y, my claim is that the expectation of x will always be more than expectation of y, right? So any thoughts on any simple example of what some for x and y which satisfy this condition? A very simple, straightforward example if you can think of. Any two random variables which satisfy this condition.
Uniform.
I'm sorry.
Uniform.
Uniform, yes, but in what sense? So there are two random variables. So what uniform? Uh, which is uniform in what sense? So one again, yes, uniform is yeah, simple example. So here basically I would say, let's say if x follows uniform of 0 1, and y follows uniform of -1 0, right? So always x will be more than y, right? And by the way, will it? So let's assume that x and y are continuous random variables, right? Just one complication which I thought you should be aware of. So let's say this example is clear, right? So for example, what will happen here is if this 0, x will always be one of the values from here, 0 to 1, and y will always be a value which is -1 to 0, right? So any value that x takes, it will always be more than y. Simple, stuff here. Um, let's say if x and y are continuous random variables, right? Just an aside here. So are continuous, absolutely continuous again, right? Random variables. So if this is true, then so x greater than y defines an event, right? That we have already seen. So so uh, this event and x greater than or equal to y event, let's say, right? These are two events. So how are these events related when these two are absolutely continuous random variables? Like, can you make some sense of what these two, how these two events should be related?
They are equal.
They are equal. Okay. Why?
Because in continuous we don't take a particular value.
Right. Exactly. Right. So this again just points out to the what we discussed last class, that so we can write this x greater than or equal to y, right, as a union of two events, that is x greater than y union x equal to y, right? This x equal to y can again be written as union of two events. Let's say x equal to a union, sorry, not union. This is intersection y equals to a, and this is over all a. So let's say this is one set. This is union over all possible a, like this, right? So again, so these two are mutually exclusive events, right? And here also these two are mutually exclusive events. And what will end up happening is when you look at the probabilities of these, this left-hand side event and the right-hand side event, these probabilities will be zero. And that's exactly because they're absolutely continuous random variables. So therefore, at least in the terms of probability sense, what will end up happening is that the probability that this event happens is same as the probability that x greater than y happens, right? Okay, so just keep in mind these small stuff. So okay, let's just never mind. Okay, so now we'll go ahead and look at this proof that if x is greater than y at all times. Okay, another slightly non-trivial example could be something like this, right? So let's say if x is uniform 0, 1 and y is, let's say, uniform 0x, right? In this way, so then obviously y is always less than x, right? So that could be another this one. So here basically the support of this y depends on what x you got from the previous this one. So there's some in some way. So these are basically your not independent as such. These two are independent random variables, right? One doesn't affect the other. Okay. So again, very simple thought process for this proof. So if x is greater than y, I can write that x minus y is greater than 0, right? And let me write this x minus y as another random variable called z. So if z is greater than 0 for all possible z's, right? That's the whole idea here. So then what is the expectation of z? Expectation of z can be seen as over all the values that z supports, right? Z into probability of z dz. So so for all z, we know that this particular term will always be greater than 0, right? Because this is non-negative. Probabilities are not probability density functions are also non-negative, right? So this quantity becomes greater than 0 for all possible values of z. So therefore, this integral as such will be a more than 0 quantity, and therefore this expectation of z is more than 0. Now, if expectation of, so expanding z as x minus y and using linearity of expectations, I can write expectation of x minus expectation of y greater than 0. And this is again some trivial algebra. And here what we have used is the idea that if I have a sum of random variables, let's say, their expectation is nothing but a sum of their expectations, right? Okay, so with this in mind, now we'll come back to this idea that, okay, so now here also I have two random variables as we discussed that f of x is a random variable and this whole expression is a random variable. So therefore, if I take expectations on both the sides, what will end up happening is I'll have expectation of f of x greater than or equal to. Now, this is a quantity which does not depend on x. And this also doesn't depend on x. And again, using linearity of expectations, what will end up happening is I will have something like this, right? Expectation of x minus a f dash of a, right? Now, the idea is just now we had just one step remaining. That is, let's say I can choose any a, right? I can choose around which point I want to expand my function to be, right? So therefore, if I now choose, let's say a as the expectation of x itself, right? Again, these are all under the assumptions that we discussed last time. That is that the expectations must exist, right? So like they cannot blow up to infinities and all, right? So if that happens, so if a is equal, so expectation of x exists, and then I choose to expand my function f over that point. So then, and when I can put a is equal to f expectation of x here, I would get the Jensen inequality just like so. This becomes f of expectation of x, right? And this term goes to 0, right? So this is the proof of Jensen inequality. Now let's say if I want to think about applying this to a concave function, how would I go about applying it? Any thoughts? So let's say if G is concave, right? So if G is concave, what happens to minus G as a function? So if G is concave, minus G is convex, right? This idea is just from the definitions of concave and convex functions. So that if you apply here, so since minus G is convex, so this I can just look at it as G of x will be less than or equal to, let's say, G of E of x, right? So this is when G is concave, and again expectations exist and double differential, all of that is implied. Okay, so this is about the Jensen inequality. Now this question of when will equality hold, that thinking in another sense, but we'll come back to it if we need. Okay, otherwise we'll see if there are other things that we require. Okay, so is this clear? Any doubts here? Otherwise we'll move on to the next concept. Okay, fine. So, okay, now let's move on to this a concept called KL divergence, and we'll see that this is the holy grail that we will use for in our discussions on VAEs, and even in things like diffusion models and all of that, which is something um, you know much more a bit more complicated than these simple models. So so KL divergence as such. So also okay. So now let's say I have a problem statement saying that okay, I have two distributions. Let's say P of x and Q of x. So over some space, right? So this x can be anything. It can be a real number. It can be a vector. All of that is fine. It's just that P and Q are some two distributions, and we want to know, we want to quantify in some way how different these two distributions are, right? And why we want to do that, we'll look at it probably today, or most probably today or next class, right? So what could be one way to look at their how different they are. So one such metric is KL divergence for that, right? There are many such metrics out there, actually speaking. KL divergence is one of them, and we'll see, how even those other different metrics can be all grouped into one single sort of a metric if we have time, right? So one such metric is KL divergence, that is, which is defined something like this, right? So let's say if so KL of two distribution, that is P and PQ, this is the symbol that we use for denoting these divergences, is basically the integral over x P of x log P of x by Q of x dx, right? So this again should be very clear from the theorem that we did last class, the Lotus theorem, that this is basically just the expectation of the function log of P of x by Q of x over the distribution of x, that is Px. Okay, so this can be seen as expectation of a function of a random variable, right? X is a random variable here. The function is log P of x by Q of x. And if I take the expectation of this function with respect to x, that is the KL divergence here, right? And obviously, again, as we discussed, that when you take expectations, it's mainly on the support of P of x. So here the distribution is P of x. The function that we are taking expectation over is this log p by q. Okay, is this clear? Okay, so now we look at some properties of the scale divergence, right? So for the first property is that the scale is always non-negative, right? It can be 0 or more than 0, right? So let's say, so we'll try proving this today. We'll try proving this now. So let's look at minus scale, right? So minus scale, if I have here, I can take this minus inside expectation, again linearity of expectations, and log of p by q will become log of q by p, right? Now, we know that log as a function is a concave function, right? So why is that, by the way? Again, simple, high school calculus that let's say if your f of x is log x, right? F dash x is 1 by x, f double dash x is minus 1 by x squared, which is less than 0 for all x. And here x for all means for all where we define x, log is defined, that is basically in the positive real number line space, right? So because this is true, this is a concave function and strictly concave, by the way, right? So this is the reason that log is a concave function. Now for concave function, we already discussed what the Jensen's inequality looks like, right? So the expectation of the function will be less than or equal to the function of the expectation. So this expectation is less than when I apply the log over the expectation of the of this function, that is p q of x by p of x, right? So this was because of Jensen's inequality. Jensen's inequality. Now, this term I'll expand and I'll write log of log integral p of x, q of x, p of x. So now how do I proceed? How do I go forward from here? From here, it should be very straightforward. So anyone want to take a chance?
P of x will get cancelled.
I'm sorry?
P of x will get cancelled.
P of x will get cancelled. But what if p of x is 0? I can't take 0 by 0.
It is PDF, so how can it be 0?
Sorry?
It is PDF.
Yeah, PDF can be 0, no? So for example, when you are discussing the uniform example that we keep coming back to, right? So how is the uniform distribution defined? So it's basically like this, right? So it can be 0, no? But are we taking those 0 points in this integration? So p as a function can be 0 anywhere and non-zero whatever. The only constraint it has is its integral should come to 1. But the idea here is we're taking this integral over x, and this x is only on the support of p, right? So wherever p of x is non-zero, only those points we're taking the integration over. So by definition of this integral that we have defined, the way we defined the expectation, this quantity will never be 0, right? So therefore this is a valid operation, right? P of x will never be 0 in this particular space that we're looking at, right? Okay, so this now then becomes log integral over x q of x dx. So now how do I proceed? Any thoughts? So see, if kl is greater than 0, what do I need to prove? I need to prove that minus kl is less than or equal to 0, right? So I need some less than, I already got less than or equal to. I just need a 0 somewhere. So any thoughts on how do I move forward from here? So what is integral of a PDF function? We just discussed this.
1.
1. So can I write this as log 1?
But the Q of X, the support is
Right, exactly. Good catch. So here we're doing something like this, right? So integral, let's say x q, if I take, that is, let's say support of q, this integral will be equal to 1 exactly, right? Now, if I so if this script x and script xq are not exactly equal, then the integral of q of x over x dx will be less than or equal to 1, less than 1, right? So it will be equal if and only if x is equal to xq, I mean the script x equal to script xq, otherwise it will be less than 1, right? So this quantity will be something less than 1, right? So log of a number which is less than 1 is negative anyway, right?
negative.
Negative, right? So this value as such turns out to be just less than or equal to 0. That's it, right? And I'm putting equal to here because we don't, I mean, we have not made any further assumptions on how script x and script xq are related. So in case they're equal, we'll get exactly log 1 equal to 0. Otherwise, it will be something less than 0, right? So this proves that KL divergence as such is always greater than or equal to 0 between any two distributions, P and Q. Okay, this is one property of KL. Another property that we have is this. Okay, so if I say that KL equals to 0, so that is I'm looking at this specific condition that KL equal to 0. So my claim is that this double implies P equal to Q, right? This symbol just means that for all x, P of x equals to Q of x. These two are identical functions, right? So the reverse implication is very clean, right? If P is equal to Q, you can simply say KL is 0. Why is that? Again, straightforward application of the definition that we have. So KL of, let's say, P Q would just be what's that, expectation over log P by Q. This turns out to be 1. Log 1 is 0. Expectation of 0 is 0. So it's straightforward. Nothing very difficult here. So the reverse implication is where we need to scratch our heads a bit. So let's say if KL is 0, how do I prove that P is equal to Q, right? So if KL equal to 0, and we just saw just now saw that this proof that KL is greater than or equal to 0. So I need to make exactly two inequalities to be exactly equal to 0, right? So I had one inequality from Jensen, right, and one due to mismatch of support, right? And see, again, we are dealing with continuous random variables only throughout. In discrete case, a lot of these things will become very a bit simpler in some sense, right? But we look at this case because this is how we're going to treat VAs also, right? Okay, so we need to make two of these inequalities equal to 0. Sorry, we need to make two of these inequalities strict. That is, we need to make them exactly equal, right? Only then this whole the steps will follow through, become equal everywhere, and then I'll get KL equal to 0, right? Which is exactly what we have as a premise here. So um, so one so this inequality should be made equal. So any thoughts on how we can go about this? So instead of appealing to Jensen's inequalities direct, thought process of, okay, how to make it this, when does equality hold and all of that, can we use the idea of log function itself purely and see when would this thing turn out to be equal, right? Any thoughts on how we can get started? Okay, so let's say so first we'll look at some the property of the log function, and we'll appeal to the derivation that we did for Jensen's inequality. Okay, that is the Taylor remainder theorem. So we say that what we finally got was something like this, right? So let's say f of x is f of a x minus a f dash of a, and then this quantity, some c where c is between the whatever, right? And then the idea here is that if f is log function, right, log is strictly concave function. So what this means is that this f double dash of x for the log is strictly less than 0, right, which is exactly what we did here just now. Sorry. Yeah. So yeah, this one, right? So so if it's strictly less than 0, so what would happen here is just the fact that f of x is less than f of a x minus a f dash of a, and this is exactly how we proceeded with the derivation, and we came to this quantity that expectation of f of x is less than f of expectation of x, right? Now if I have to make this equal for the sake of this log function, so what is the only thing that is like, what could be the only thing that is possible that could make this to be equal? Any thoughts? So as we saw that, this
When x is equal to 1.
right, है So now what will happen is, let's say if x is a random variable, that is true, but if x was random such that x always takes only one, right? So it takes one with probability 1, right? It's only one. So in a sense, it's not random in that sense. So here the idea is that, so if that was the case, then log 1 becomes 0, expectation of 0 is 0, and this is 1, so log 1 is again 0. So if this happens, then this inequality becomes equality, right? So then I would have expectation of log x equals to log of expectation of x, right? So this implies that if I have to, make these two, make this inequality strict, what I need to have is that q of x and p of x should be exactly equal, right, for all x, right? So this implies for our proof that p of x should be equal to q of x for all x, right? Okay, this is one. Then what about the second issue, mismatch of support? By the way, does this issue exist anymore under this thought process?
Support is same.
I'm sorry?
Support is same for both.
Support has to be same, right? So there cannot be any point x which is such that q has some non-zero probability there, but p of x doesn't have a non-zero probability there, right? Because the fact that again, okay, this is a bit confusing. So, okay, let me just make it a bit clearer. So again, see here we are looking at expectation over the support of p. So what we have done, we have said, okay, p of x equal to q of x for all x belonging to the support of p, that is this script x, right? So when you do that, there leaves some room for doubt that, okay, outside the support, can q of x be something else, right? But that is not true, because of the fact that when I take integral over x, the same x, if I take integral over p of x, this is equal to 1. This implies the integral over x, q of x also has to be equal to 1, right? So this q of x, this q cannot have any point outside this particular script text where it has a non-zero value, right? So therefore, the support for P and Q has to be exactly the same, which is this script text, right? So there's no support mismatch issue also anymore. So this makes sure that if KL is 0, right? So if KL is 0, this implies that double implies that P is equal to Q always. KL defined as above. Okay. One another property to note is that it is not a symmetric metric, right? It's not a symmetric sense of a measure of the difference between two distributions. Again, that can be seen from the formula itself, and this can cause some issues. Okay, and we'll look at if we touch GANs, we'll look at how this can cause issues in GANs a bit. But the idea is it's not symmetric. So there are there are some ways to try to make it symmetric. There's something called as JS divergence, also called as Jensen-Shannon divergence. I mean that's the Jensen-Shannon divergence. This combines the scale in the forward way, which is so-called P given Q. So I can write KL PQ and KL Q and P, right? Obviously, I can look at this divergence also. So it looks at some sort of a combination of both of them, and this becomes JS of PQ, right? Yeah, the exact formulation I'm blanking on that right now, but yes, so this is something you have a plus sign, but yeah, there's some other terms here and here. Again, so we'll come to that when we need it. Okay, so Jensen-Shannon as such solves for this non-symmetric sort of an issue with KL divergence. And why more than anything it's an issue because it doesn't sit with our thought process of distances, right? When you say distance we think of it as a symmetric quantity. Even the mathematical way of defining distances in in spaces all we consider them as symmetric measures. So KL not being symmetric violates that intuition of a distance as such, right? That's the only reason. Otherwise, there's no a problem with it having not being symmetric and stuff, right? Okay. Uh, cool. So this was about the KL divergence and its basic properties. And now we'll look at a special case of a KL between two Gaussian distributions. Now, why are we doing this? Is because we'll be dealing with Gaussian distributions a lot again in the coming classes, and this particular formulation helps us circumvent a lot of sampling issues. And again, we'll come to that when we discuss VAs. I'll tell exactly where it helps and all of that, right? So we'll derive this thought process of KL between Gaussians. How can we derive that using say, some simple algebra and stuff? Okay, so let's look at two multivariate Gaussians. Okay, so let's say if I have P of X defined as, again we did we looked at the um, formulation for multivariate Gaussian distribution in the last class. So let's say this is exponential of x minus mu p transpose sigma p inverse x minus mu p, right? So where and a better way of writing this is, let's say probability of x mu p sigma p. So mu p and sigma p are basically the mean, right, and the variance covariance matrix, right, for this distribution that is P, right? So I have two parameters here. Same thing, I have another distribution which is also a Gaussian distribution, right, but with its own parameters. Same formulation. So now what we want to do is we want to look at what is the KL between these two distributions, right? right? And by the way, so if you just draw your attention here, so sigma p, sigma q, basically there are let's say, so what does d stand here, by the way? So d is the dimension of x, right? That is basically, we say that x belongs to, let's say, RD space, right? And your mu, and therefore your mu q, mu p, the mean vectors will also belong in this space, and your variance covariance matrices will be a D cross D matrix, right? D cross D matrix, such that they're invertible and all of those nice things. So, so this term basically is a scalar quantity, right? Why? Because and we say that this x is a so for us all vectors, when looking at in terms of matrices, we'll treat them as column vectors, right? So x minus, let's say, mu p or whatever, this is a column vector of d cross 1, right? So when I take transpose, right, this becomes 1 cross d. This sigma q inverse or whatever, sigma p inverse is a d cross d matrix, and x minus mu p is d cross 1. So this gives you a 1 cross 1 scalar quantity, right? Some scalar quantity. And this is what goes into this exponential, and therefore this is well defined. This is a number again, so this is just a function which takes a vector and spits out a real number, and such that the integral of this q over this space RD is going to be 1, right? Okay. Now let's look at the KL between P and Q, right? So this can be seen as integral, or we'll do it a bit easier. So this is basically expectation over, this P of x as a distribution of the quantity log P of x by Q of x, right? So this is expectation over P, omitting the of x for now. So log P of x by Q of x, as you can imagine, that these two will just go out, and P by Q, right? So I will have sigma Q power up. So I will have here log of this quantity, right? Sigma Q power half, sigma P power half, right? And then I'll apply log internally, and this would turn out to be something like this, right? So P transpose sigma P inverse minus mu P plus half x minus mu Q transpose sigma Q inverse x minus mu Q, right? And this can then be written as expectation over P. So half of log of sigma Q by sigma P minus this whole quantity. And again, using the idea of expectations being linear, right? So I would just skip one step and go right ahead with this. So this is a quantity which does not depend on the probability distribution P, right? So this I can just return it as half log, half log this, right? This quantity is now to be taken expectation of this one, transpose. Just stop me if anywhere it becomes unclear, right? Expectation over P x minus Q. Right. Okay. So let's go term by term. This term is anyway nothing more to think about here. This is term 1, this term 2. So term 1, if I had to expand, So what we can do now, so we think about it, this expectation is over this quantity. So as we spoke just now, that this is scalar quantity, right? With three matrices multiplying each other. This is you can think of it as a row matrix, a square matrix d by d, and this is again a column matrix, right? So if I were to look at the so if this is a scalar quantity, x minus mu p transpose sigma p inverse x minus mu p. So I can write this is basically a scalar quantity, so I can just write it as a trace of itself, right? Right. So this can be seen as a 1 cross 1 matrix in some sense, right? So I would have it as trace of this. Now we know in trace there's a property of the matrices that if trace of ABC, I can write it as trace of BCA, right? Or trace of, let's say, CAB, right? So these are rotation invariant, right? So we'll use that sort of thought process and we'll change this to trace of sigma p inverse into x minus mu p into x minus mu p transpose, right? So what we have done, so this is the matrix A, matrix B, matrix C, right? So I've taken B, C, A, right? Now, so trace operator, right? Now, if you think about it, I have integral of this, so expectation of this quantity, right? So I have expectation over P of this trace. Right, and by the way, so this matrix is again a d cross d matrix, right? So because you'll have d cross d here, this is d cross 1 into 1 cross d. So this is a d cross d matrix. We are taking its trace. So finally, we'll get a scalar. So we are good there, right? Now we know that through linearity of expectation, so trace of something is basically just sum of the diagonal elements, right? So that sum, I can what I'm doing is I'm taking that sum's expectation, right? So I can always look at the sum of the expectations. So this can be written as trace of the expectation over this probability p of x, right, of this quantity, right? There is one subtle thought process here, that this expectation now is going to lead us to a matrix. Okay, so here this was a matrix. You take the trace and then you have to do an you take an integration over it. Here the idea is that you're taking a trace of this being a matrix, and then expectation also gives rise to another matrix that that matrix what you get after expectation, you then take its trace. So now what we'll do is we'll do a bit of jugglery here, and this can be written as sigma p inverse into this expectation of this quantity, right? Expectation of p, right? Okay, so again, this is because sigma p inverse doesn't depend on the probability distribution, right? It is known. It is fixed for a p of x that we have, right? So this now, by the way, so what does this expectation look like? Any thoughts?
Variance.
Right, the same variance covariance matrix, right? So this is exactly sigma p only, right? So sigma p into sigma p inverse. So this is just basically identity. So what is trace of identity in this case?
depends on the dimension.
I'm sorry.
It depends on the dimension.
Right. So and we already discussed what dimensions it lies in. Is the RD space. So this will just be D. Right? It will just be D. So my second term turned out to be a very simple term. Though it looks very complicated, it is just minus D by 2. Right? We ignored the half, so it's just minus D by 2. So the first the term number 1 turns out to be D by 2. Okay. The second term is very similar to this, but there is some complication. So we'll see what the complication is. So let's tackle the second term now. So expectation of P. What we did, yeah, x minus mu q transpose sigma q inverse x minus mu q, right? Again, we'll do the same thought process, everything, and what we'll end up with is something like this, right? So it'll be trace of sigma q inverse of expectation over P of this quantity. Now, is this something that you that we know? Again, this is the expectation and this is the trace. Yeah, okay. So this term, do we know? Is this can I write as sigma P inverse? Sigma P, sorry.
Yes.
Are you sure? So what are we taking expectation of, right? That's the biggest question. So here we had expectation over x minus mu P, right? Here is x minus mu Q, but over the probability distribution of P. So this quantity is not sigma P, right? Sigma P, that is your variance covariance matrix, is defined as the expectation over that particular data's mean, the distribution's expectation and stuff. So this is not exactly this quantity at all, right? So we need to do something about this. So one very simple thought process is that we just subtract and add mu P to make it a bit simpler. So we'll just look at that term for now. So x minus mu P plus mu P minus mu Q, right? Into the same plus mu P minus mu Q transpose, right? So I can look at this as two terms like this, right? And oh, sorry, yeah, look at two terms like this, and this can now be seen as, so I have a plus b into a plus b transpose. So I'll just have a and this, so I'll have x minus mu p into x minus mu p transpose. This is a term that we like, right? Because I can take expectation over p and get my sigma p. Next, what term I have? I have this, so x minus mu p into mu p minus mu q transpose, right? Same term again, but yeah, x minus mu p, and then mu p minus mu q, mu p minus mu q transpose, right? Okay, so now if you take expectation over this, what would be the result? Any thoughts? First term is simple, we just discussed. This is just sigma p. Okay, what is the next term? No thoughts?
Zero.
Zero, right? Why? Because your mu p minus mu q transpose is a constant quantity. So I can take the expectation inside this term, and I would have expectation of x over p over the distribution of p, which is same as mu p, right? So both of these terms will become zero, and that is because So expectation of x minus mu p into, sorry, into mu p minus mu q transpose can be written as expectation of x minus mu p into mu p minus mu q transpose. This by definition is 0. Okay, so we define mu p. And then finally what I have is expectation of p with of this, right? Again, this is a constant quantity, so this is just going to be mu p minus mu q into mu p minus mu q transpose, right? So this term, that is this term we have done till now, right? So my second term as such, so we'll now, let me just put it down here. Yeah, so continuing. So what I get is this becomes equal to trace of sigma q inverse I had in the top into this quantity sigma p plus just a moment, sigma p plus mu p minus mu q into mu p minus mu q transpose, right? So this becomes trace of sigma q inverse sigma p, right, plus again trace of sigma q inverse of this. I can again reapply the trace thought process and I can get it in this form, right? So there is sigma p q mu p minus mu q transpose sigma q inverse mu p minus mu q, right? So my second term at the end of the day becomes half transpose this plus half of this. Right now, yeah, so the KL term finally, so KL between P and Q, if P and Q are both Gaussians, it turns out to be half log sigma Q by sigma P differentials, and then this was minus, right? Yeah, minus d by 2. So minus d by 2 plus half trace of. So how does this help us is basically now if I want to calculate something like this, right, where I have two Gaussians, and why that will be is because we'll be dealing with Gaussians a lot by formulation. So what will end up happening is that if we want to calculate something like this, we don't have to go about this roundabout way of looking at this integral, solving this integral over and over again. Rather, if you have two Gaussians, you can deterministically calculate their KL divergence, right? So this is supposed to give you a number, that is how far these P and Q distributions are. And again, this is sort of very intuitive, that let's say you already know the shapes of the two Gaussians. P and Q are both Gaussians. What differs is their mean and their variance, right? So as you can see, with all the terms which you see here are basically in terms of their parameters, that is mean and their variance, right? And both affect in a bit complicated way of how you can view whether these two distributions, how different these two distributions are, right? Okay, so that's a thought process with KL divergence. So this is where we'll close our discussion on KL divergence. All right. Now, so this okay. So now we'll go into some thought process and basic requirements for this VAEs and stuff like that. So so what we want to do, the course name also has generative modeling using VAs. So what does modeling exactly mean, and what assumptions are you working under, right? So let's say you have you want to build a model. So what is statistical machine learning as such? what is its core assumption for building a model and stuff like that. That we will discuss, right? So statistical ML has a core assumption underlying it. So any thoughts on what that assumption is? You might have heard this somewhere if you know. What is the core assumption that statistical ML depends on to do all of its work for now, till now? Oh, by the way, any doubts in this part, KL divergence part? Anything unclear or? No, right? Okay, fine. So coming back to the question, so so the core assumption that statistical ML depends on is so let's say you're dealing with images, right? For example, let's say you have images of dogs and cats and stuff like that. So what you have is basically some data, right? And let's say I'll represent the data as X, right? So what ML tells you is that X is basically a random variable, right? And it has an underlying distribution, right? Underlying and generally unknown, mostly unknown distribution, right? And whatever images that you have got, for example, let's say if X is, for example, let's say an image, right? So whatever images you have got are samples from this particular random variable, right? For example, let's say you have taken your Nikon camera and you have a lot of images with you. So what ML tells you to the way to treat those images is basically that all of these are just let's say you have some 100 images, then these are all just samples coming from this random variable X. And for our case of our whole discussion, we'll call that distribution as Px. Okay, so this Px is the underlying distribution from which you're getting your data, that is whatever data that may be, right? So for example, it could be audio samples, or it could be brain images, or it could be your usual images as such, right? Or it could be Titanic data set, right? All of these basically, they follow some unknown distribution, and whatever data you have is just a sample from that distribution. Okay. Um, so then what does modeling mean is that, for example, let's say you want to understand or approximate this Px in some way, right? But obviously you don't have what Px exact form is. Rather, you will look at this. You will try to use some parameters, let's say theta. Okay, so some parameters, theta, right? To which basically characterize a distribution called as p theta, right? So they characterize a distribution called, we'll call this as p theta, right? So our goal, in some sense, is that we want to make these two distributions, that is px and p theta, very close to each other, right? Obviously, because because we don't have any because we don't know the exact form of px. What we want to do is we'll approximate this px with some p theta, right? And while trying to approximate, we want our approximation to be as good as possible, right? So therefore, our aim is to make p theta as close to px as possible, right? So then we just today discussed one way of looking at what how these two distributions are different, which is your KL divergence, right? So let's look at this quantity. that is KL divergence of Px P theta, right? What would this mean? And let's look at some implications of this particular thing. So KL of Px given P theta. So let's just expand that. So I would have I will take the expectation over Px, right? Log Px of x, right? And divided by log P theta of x, right? P theta of x. So this now can be written as expectation over Px log Px of x minus expectation Px log P theta of x, right? So anyone know what the first term corresponds to? What does this term correspond to? Again, not necessary to know this, but just be aware what this is. So this is the entropy, basically, negative entropy, by the way. Symbol is H. So entropy of a distribution, right? So actually, let's look at it as in this properties of random. Yeah. So let's say I have a distribution. Let's say I have x, which varies with some f of x or p of x as a distribution function, right? So, and again, it's a continuous random variable. This is a probability density function. So if I want to know the entropy of x or entropy of p of x is basically defined as like this: p of x log p of x, right? Log p of x is always going to be yeah. So this quantity as such will turn out to be a positive number, right? So entropy is always greater than or equal to 0. Okay. So this is called entropy. Now here again, it doesn't matter much, but just know that this is there. And then we have expectation of p of x log p theta of x, right? So so when you're building a model, and this is the general method that we will use everywhere. So the idea is that because p theta is characterized by theta as a parameter, so if I want to change p theta, it makes sense that I need to just keep on changing theta, right? P theta, p theta's form or p theta's values for every x depend on theta. So if I want to make p theta as close to px, the burden basically falls down on theta. So if you keep on changing theta, you get new p thetas, and then you can see how close this p theta is to px, right? So therefore, what we want to do when I want to make p theta close to px is I want to so the goal basically turns out to be I want to minimize the KL divergence between px and p theta, right? But minimize how, right? That is over theta. Okay, so basically the idea is that keep on changing theta such that p theta and px become as close as possible. So as you can again very clearly see that this first term doesn't depend on theta at all, right? Because it's the inherent property of the underlying data distribution. So this basically turns out to be just minimizing over theta expectation of p of x log p theta of x, and this basically just turns out to be maximize theta expectation of x log p theta of x, right? So now there's a special name to this. I mean, so log so p theta of x, right, is the model likelihood, right? Model likelihood of X, right? So it's telling you what is the probability density value for X under the model theta that we have in place, right? And log p theta is called as log likelihood. So what we are saying is that if you try to maximize the expected log likelihood of the model, right? That is equivalent to saying that I'm minimizing the KL divergence between the actual distribution that is Px and the theta that we have, the model that we have P theta, right? And thus, if I make my goal of increasing this quantity, I can I'll try to become as close as Px, right? So my model will become as close to Px as possible, right? This is the idea for your generative modeling mainly, right? Now, so then the question comes, okay, we have this some parameters that we have in place. So what parameters could they be, and how to uh, optimize this particular thought process. So now we'll turn to neural networks for help in terms of this approximating this log likely the px that we have in place. So the way we are going to look at neural networks is as a function approximator, right? Now, there is a theorem which says that neural networks are basically universal function approximators, right? So let's say in any place in this whole derivations of VAs and wherever we do, so wherever we need to approximate any function as such, what we will end up doing is we'll say, okay, I have a neural network which can take which can approximate any function, and its parameters is what we will try to learn, right? So our model will turn out to be a neural network for the sake of function approximation, right? And then function approximator. And because neural networks are again characterized by their parameters, that is theta. So our theta basically is just the NN parameters, right? So all your weights and biases, etc. So all of those will come as the parameters for this neural network, parameters for this model, and that is what we want to, update or change or optimize such that my p theta of x becomes as close as possible to px. That is the underlying distribution. Okay, so it's all well and good, right? So we saw KL divergence, and we're trying to minimize the KL divergence, maximizing the log likelihood of the model. But there's a small issue here. So if I were to expand this expectation, right? Let's expand this expectation, log p theta of x, right? So this turns out to be px of x log p theta of x dx, right? So anyone can see what the issue is in this formulation? Can I just go ahead and do this integral as it is? What's the thought process behind? I mean, so can I just go ahead and plug in values here and look at this for every for a given amount, for a given values of theta, and then choose any algorithm which updates my theta based upon how far I am, right? Or keep increasing, go in the increasing direction, and make sure that I keep on going and closer to px. So what's the issue in doing this sort of integration? Any thoughts?
P theta of x is also depend on x,
Depends on
the support.
Depends on x. Yes, correct. That is fine. So, but that's fine, no? So because I'm looking at only in the support of x. So let's say if I were to, so the basically because p theta, let's say, okay, you're saying that it's a neural network. So I mean, I don't have a fixed support for this neural network. Neural network, whatever you give input, it'll spit out some output, right? So, but that's fine for me because what I'm doing is I'm taking the integral over only x. So outside this x, I don't care how the neural network behaves, how p theta behaves, whatever. That will be an issue when we go internally. That we will deal with later. But that's not the issue here, though, right? Because in integral is well defined. I mean, I look at the support of x. P theta of x need not be 1 under the support of x. That is also fine. What other issue would you see here? So think about this term. There's something special about this term being here, and they're just causing a big problem. So do we know the functional form of px, by the way? If I have to integrate, I have p theta, right? Because theta is controlled by me. I know what parameters are. I know what p theta is. So I can do log p theta of x for any x. I can calculate this value, right? But do I know what px of x is?
No.
Right. You know. So that's the issue. So our whole problem that we had was that we don't know px of x. It's an underlying distribution that we don't know. We just have samples from it, right? So this integral evaluation is not possible, right? So rather than going this route, what we will look at is we will try to approximate this expectation itself. And there is one standard way of doing it. I mean, one of the ways to do it is looking at Monte Carlo estimates, right? So this basically the idea is that I want to know the true mean of this function, right? I'm looking at expectation of a function of a random variable x, right? But I don't, but I can't calculate this expectation in a closed form or whatever, right? So rather than trying to do that, what the other way of doing it is that I can look at samples from this px, right, and calculate something called as the sample mean, right? So let me just put this as a separate, or okay, let's just take an aside here itself. So okay, so the idea is, let's say I want to get this expectation as expectation of f of x. For some reason, I cannot calculate this in closed form. So what I will do is I'll take samples from this particular px, right? Let's say I'll take n samples from this px, okay? And I will calculate the sample average. So f of xi, I going from 1 to n, right? So if I can evaluate the function f at multiple points, where these points xi are sampled from this px distribution, right? This is again an approximation, and there is a theorem which tells you that this is okay to do. Any thoughts on what the theorem is? Okay, in the sense, I mean, yeah, like there's some theorem which tells you that this is still not so bad thing to do.
Weak law of large.
Weak law of large numbers, right? Weak law of large numbers. So what this tells is basically, in one line, if we have to understand it, is that as n tends to infinity, the sample average will become close and close. That is, it in the limit of n tends to infinity, sample average will be the actual mean, right? True mean, right? So we want the true mean, right? True mean of this function f of x with respect to this distribution x. If I have large enough samples, I can look at the sample average of this function, and this will be close to this if n is large, right? That is the idea that we are going to use. So now, okay, then the question comes, do we have samples from this distribution? Yes, we do, right? Because that's the exact core assumption that we had discussed in this page, right? That is, I have whatever data I have, I'm assuming that these are basically just the samples from an underlying distribution. So I have, let's say, n samples from this distribution, right? So what I can do is I can calculate this quantity now, the quantity being this I equal to 1 to n log p theta of xi, right? For all these i's which already have samples, I calculate this. Now this will be a function of, any thoughts? Function of what? This will be a function of what? Will it be a function of the data?
Theta.
Sorry?
Theta.
Theta, right? It's going to be a function of theta, right? And inherently, yes, inherently it's a function of the data that we have in hand. Let's say I'll put it like this. But yes, I mean, given the data is fixed, we're not messing with the data anymore. So this is just a function of data, right? So it can be seen as some f of theta, right? Now, if I want to apply, for example, let's say, if I use neural networks, what is the standard way of updating thetas is using gradient descent methods, right? So gradient descent you can apply. I mean, in this case, ascent, because you want to maximize this function. Or one second, let me just put it as gradient descent on minus f theta, for example, right? And then update theta using this procedure, right? So what will this make sure? So you're updating theta in a gradient descent of minus theta. So we are in a way maximizing f of theta. F of theta is basically the sample average of this model log likelihood. That is the approximation to the actual model likelihood. There is the expected model log likelihood, which basically, if you maximize, you are that's equivalent to minimizing the KL divergence between Px and P theta. We know from KL divergence properties that if Px and P theta, if the KL divergence becomes 0, you will end up having P equal to Q. That is, your model will become exactly equal to Px, right? So if this becomes close to 0, if this becomes equal to 0, then you have approximated your Px, take them perfectly, 100% 100% replicated, right? This is the story that we have been sort of building upon till now. Okay. Right. So any thoughts, any doubts, anything confusion, how something is related to the other, anything else you want to know until before we move on to the next concept?
So why are we not directly estimating the theta with the samples?
With the samples you want to estimate?
Theta. The
Theta.
parameter.
Yeah, no. So theta are basically like, let's say, for example, thousands of parameters you might have, right?
Okay.
So the idea is these parameters, they give a shape to your p theta of x, right?
Yeah.
And when you're trying to make this p theta of x equal to px, you're also modifying the shape. Shape, the values, everything, right? That's the thought process. And therefore you hope that it'll become equal to px or whatever, right? That's the thing. Now what I've given you an example is that, okay, theta is some parameters, theta is neural network parameters and all, but it need not be neural network also for that matter, right? I brought up that because VAs, that's what we're going to use, but theta can just be, for example, something like a Gaussian mixture model, right? So I would, let's look at this example. Let's say I would say that P theta of x, okay, is a Gaussian mixture model. Gaussian mixture model. Let's hope I remember. Pi. Let me use k, small k and capital K. Okay. Um, x mu k sigma k. Yeah, this looks right. Okay, so let's say p theta of x. Like, see, so this is the point of coming to modeling, because modeling, in the sense, you can choose the shape, the form of p theta of your p theta of x in any way you want, right? So let's say I choose that p theta of x should be a Gaussian mixture model, right? So if this is the case, then your theta ends up becoming these values: pi k, mu k, sigma k, where k is from 1 to capital K, right? And the way you will update these parameters is using the EM algorithm, right? This is another side story altogether. We can go into it if you guys want, but that's the thought process, right? Now, what we have chosen is that we have chosen this way of looking at neural networks as function approximators. So whatever the way neural network changes is through its parameters. So its parameters become the model parameters for our use case, and that modifies your p theta of x. Yeah. Okay. Anything else? So how all of this is tying up till now? So till now, I guess what all we discussed till now, all of that boils down to this idea that I want to make a function. I want to make a model's likelihood function, that is PDF function, close to the PX, the unknown underlying distribution, right? So then how do I go about doing it? It's something using this method. Yeah. Uh, okay. I guess this is what I had for today. So okay, let's look at some ways of sampling before we go into generative modeling problem statement. So next class we'll start with the generative modeling problem statement exactly, and then build the exact math for various for VAs. Um, um, okay, so let's look at this thing. So, okay. So let's say in your computer, if you want to, sample, let's say x from a Gaussian distribution, right? Let's say 5, 3, univariate Gaussian distribution, right? So if I want to do this, um, how, let's say, how would you go about, doing this, given the fact, okay, let's say I'm asking you to sample a value from this normal 5, 3, given the fact that I have a function which can give you a sample from uniform 0, 1. Okay, so this is all that you have with you, but you want a sample from this distribution. So any thoughts on how this happens? And we've actually covered a bit of this already in the Lotus theorem and stuff like that. Again, so I'm not looking for the exact math here, but what is the thought process that you would even think about going about this? So we're not trying to derive anything, but what is the thought process that you will have if you want to do something like this? No. we have already we talked about this function of a random variable, right? So we know that now y is uniform distributed, and what I need is an x, which is, let's say, like this, right? So if I can find a function f, right, which takes y as the input, right? Now f of y is also a random variable, right? Now if I constrain this random, I want this random variable to behave as x, right? So if I can find a function f which transforms my y into an x, right, such that y is uniform 0, 1 and x is, let's say, n503, I'm done, right? Is this true or not? Right? So
Yeah.
right. So now the thought process is, let's say, so in this case, you can solve it very easily. You have, whatever, like simple formulations given to you, so you can hope to find this function f and so on, right? Now let's say, in our use case that we have, what is the thought process is, let's say I have a random variable y. Okay, this becomes a bit challenging actually. So let's just look at, yeah. So let's say I have a random variable x, which is from px, following px distribution, right? And I have a random variable, let's say y, which follows, for example, let's say Gaussian distribution, n0i. So this is a random vector, mean 0 vector, and the covariance matrix is I. Okay. So now, if if I could find a function f, right, which takes this y as input, right, and gives me a sample of x, right? So if I do this, can't I generate more samples from of px? I can, right? Because I can sample infinite values here, and actually speaking, uncountably infinite values here, right? So because this function maps this n0i to px that I have with me, right? So I keep sampling something from here, put that through f, and I get a sample of corresponding to px, right? So imagine, so let's say, for example, I have 100 dog images, right? Now what I want to do, what I can do rather, is try to find a function from y to this dog images distribution, which I don't have, by the way, but still I'm hoping that I'm able to approximate it well or whatever. So then the idea is that I keep on sampling from this y distribution, from this n0y, and I know how to sample from here, right? So if I keep on sampling from here, I can keep on generating more dog images, right? Now the issue is this. The issue
Yeah.
is, if
Right.
I'm sorry,
You are right.
right? Anna. So I can keep on getting values from n0i. I can keep on generating more and more dog images. I don't need to have a camera anymore, right? I had a camera, got 100 dog images. Let's say, I can get this. Now the the issue lies in this fact that I don't know this function f, right? I need to estimate this function f. Here I can estimate the function f very easily. Simple distributions, known distributions, all of that. Here one is unknown distribution. I don't even know how this behaves and so on. That is where we are using this neural network, right, as a function approximator. So basically, the idea is that there is a true function f. There is some function which is f, which is true, which exists in nature, right? and which can take a n0i sample and convert to a dog image for me, right? But we don't know that function. Neither do we know the true dog distribution, true dog image distribution underlying, right? So what we will do is, our hope is that using these samples, right, which I got from PX, right, I hope to build a function approximator. So in some sense, I'm saying, okay, I want to uncover the true f. I don't have the true f. So I will build an approximator to f, that is f hat, right? Now this f hat, at least for neural network function, neural networks, is basically just a function of its parameters. That is, if I know theta, I know what f hat is. If I know f hat, I will know what is theta. So basically, if I know theta, I'm enough. That is my function approximation. And however they are connected. For example, if they're connected as a using ReLU or whatever activation function and all of those stuff that we have in neural network literature, whatever they do, I know exactly what my function f hat is going is behaving using these theta parameters, and that will basically convert a n0i, that is a sample from Gaussian distribution, to a dog image, right? So with this, I'll uh, leave you thinking about how you would build a function f, and this will lead us to our next section, which is VAE formulation. Okay, so we'll do the math next class, right? And more than that, actually, before that, we will have to do something called as variational inference. A bit idea about this, and then we'll move on to this. Okay. Cool. I guess that's it from my side. Any doubts? Anything you want to ask?
Any resources or books?
Uh, um, books, no. So we'll okay. I'll post a paper link which the original authors of VAs. So you can just go through that paper. They actually do a fair amount of explanation and also math behind what and will mostly follow their derivation and stuff like that. So I'll post a paper link. You can just go through that before the next class. That will surely help you understand, breeze through what we are doing, and also clarify in case that paper was confusing or whatever. We can discuss the doubts in more detail. Yeah.
Yeah, sure.
Okay. So let me stop the recording. I guess we are. Yeah. So just. Yeah.